set up the computer first. And let me introduce the first. I'm Wally from TAU. And each team includes your team member.
Good afternoon, dear resident fellow competitors. We are Junior from Stage 高中, and I am 张亚成, 徐德仲, 陈怡俊, 杨佑宇, 赖志荣.
And I'm Kevin. My name is Untitled. This is our teammate. 这群有南凯、陈雅茹、陈明浩。
My name is Ted, and this is I run with Omega.
We are Untitled Chapter American School. This is Thomas, Darren, Richard, and Cedric.
Okay. Because the problem also set up, so now we just beginning the 5 minutes preparation. So all the competition is money. Each team, please write down your name on the blackboard.
So I would like to begin my presentation. Good afternoon. I am Arthur Chung from Team Miracle, and I will be presenting problem 15, boycott effect. So the problem statement says that if particles are suspended in a liquid that has lower density than the particles, then they will settle to the bottom of the container. The rate of settling can be affected by tilting the container that holds the liquid. Explain this phenomenon and investigate the effect of relevant parameters. So we think there are three key questions. What is boycott effect? How does boycott effect form? And what parameters affect boycott effect? And this is our typical conference. First, we'll go over our experimental setup, and then the characteristics of boycott effect, and then we'll go over the theory and our own explanations. And here, we'll introduce the relevant parameters, and finally, we'll show you our results varying the tilt angle, the viscosity, and the roughness of the walls of the container. And finally, we'll relate our theory to experiment conclusions. So this is our experimental setup. The left is a photo of our camera setup, and the right is a photo of our acrylic settling vessel. And throughout our entire experiment, we used silica set that's 80 to 120 mesh. And in order to quantify the settling rate, we use tracker to track the luminosity. And also to analyze the flow field, we use PF5. And here's the phenomenon demonstration. And as you can see, the settling rate for the tilted container is faster than vertical settling. And also, individual particle velocity is intense. And there are several commonly used terms in this presentation. So the clear fluid layer is close to the upper facing wall, and it does not contain any particles. And the top layer is often not clear, but its descent represents the settling rate. And this is the PNK theory. PNK theory was developed to describe the rate of settling geometrically. So St is the volume settling rate. It is the velocity of an individual particle times the effective settling area. And by tilting the container, we increase the effective settling area. So the volume settling rate should also increase. And V0 here is the velocity of the particle calculated with the Stokes settling speed. And St is equal to the change of height. And by integrating both sides, we get the height as a function of time. So PNK can predict the settling rate accurately when these two conditions are met. That is, the Reynolds number approaches 0, and when lambda, the ratio between Grashof number and Reynolds number approaches infinity. In this analysis, the settling velocity of an individual particle stays the same, and that is already different from our observation. So we can already conclude that when you tilt the container, the sedimentation rate is intense. And also, there's convection where the fluid near the upper facing wall rises, and the sediment near the lower facing wall settles. And also, there's a sideways velocity that is not caused by gravitation. And in this video, you can see that some of the particles are being brought upwards by the clear fluid layer. And we will be calling this effect instability. And finally, for a large tilt angle, the clear fluid layer, that is this layer right here, is also larger, as shown in these two photos. So there is convection PNK theory where the clear fluid layer rises, but it does not explain how this convection forms. And also, PNK's theory does not explain the sideways velocity that is not caused by gravitational forces. And also, instability is not considered in PNK. So our explanation for convection is that when you write out the dimensions Navier-Stokes equations, you get this term, and that is the buoyancy force that acts on a fluid parcel. And lambda was already defined. And phi here is the local particle volume fraction over the initial particle volume fraction of the suspension. So in the clear fluid layer, there are no particles, so the volume fraction is 0. And this buoyancy term becomes negative lambda G. This points in the opposite direction of gravity, which is up. So the clear fluid rises. And for the sedimentation layer, phi is very large because the sediments are very closely packed. So this term is negative. And this entire term points in the direction of gravity, which is down. And these two combined provide the explanation for convection. And for sideways velocity, when the particles settle, an equal volume of water has to rise up to fill up their spaces. And when this part in the initial state of settling, the particles fall vertically for a small distance, creating a clear fluid layer. Water then seeps into this clear fluid layer sideways. And this drags the particles sideways too. Okay, so in order to verify the sideways seepage of water, we conducted an experiment injecting ink into the suspension layer of the fluid. And here's a video. So initially, the ink drifts to the left. And then it is brought downwards by the convective motion of the particles. And when the ink nears the upward facing wall, it is brought upwards by the instability. So this confirms that the water does exit into the clear fluid layer sideways. And our final explanation for instability is that because most of the water exits through the clear fluid layer, it has large velocity. And because the clear fluid layer is thin, the velocity gradient is also large. And because of this velocity gradient, the viscous force pulls up the nearby suspensions. So our hypothesis is that for a larger tilt angle, there's a thicker clear fluid layer, which should make this sedimentation layer, the suspension layer, more stable. And for smaller angles, we should be able to observe larger instability. So here are all parameters. We changed the slow settling speed of an individual particle by adding glycerol, and we also changed the tilt angle. And finally, we made the upper wall rough. And here's the result, showing the gray line is our theoretical prediction calculated with the slow settling velocity, and the blue line is the experimental luminosity change. And as you can see, for the initial stage of settling, the two lines actually match nicely. So this supports our use of using luminosity to represent the amount of sedimentation that is still in the suspension layer. And for the larger tilt angles, you can see that this sedimentation rate is also larger. And that is, we can tell that by the slope line here. And we didn't find the optimum angle for the sedimentation because we were trying to explore the sedimentation rate for less viscous fluids. So if we tilt the container too much, then most of the particles will settle to the bottom facing wall instead of settling to the bottom. And for here, you can see that for smaller angles, there's actually a small rise in luminosity for the later stages of settling. And this is because instability brings up some of the particles, and it takes some time for it to fall to the bottom facing wall. And here are two videos showing the instability. And as you can see, for the smaller tilt angle, the instability is also larger. And finally, we vary the viscosity of the fluid, and this changes the slow settling speed. And here are two lines showing the luminosity change for 10 degrees tilt. And not surprisingly, the container with the slower particle velocity has a slower settling rate. And because we want to cancel out the effect of the individual particle velocity, we divided the time scale the time by the velocity of an individual particle. So let's say if a particle settles for 1 meter per second in one container, and it settles for 2 meters per second for the second container, then we will scale the time by 1 and 2. And if the boycott effect is the same for these two containers, then these two lines should match. And here are the results for different tilt angles. And you can see that after scaling, the lines match quite nicely. So this tells us that viscosity does not affect boycott effect much, except it changes the individual particle velocity. And finally, we wanted to make the upper wall rough because one very important characteristic of boycott effect is that most of the water rises in the clear fluid layer. So if we figured out a way to impede the fluid from rising, then we should be able to affect the settling rate significantly. And this is the same with hot fluid dotted over ring. And we keep this to the upper facing wall. And you can see that with the rough upper wall, the sedimentation rate actually decreases. So this confirms that the rising of the clear fluid layer is actually a very important factor for boycott effect. And also we can see that the blue line actually rises a little bit and then falls again. But for the rough wall, it does not rise. This is because when we make the upper more rough, the velocity of the clear fluid layer is also smaller, and the drag force it produces on the suspension layer is also smaller. So this causes less instability. So for conclusions, what causes boycott effect? Boycott effect is caused by convection and an increase in the effective settling area. And what's not predicted by PNK is that there's the convection and sideways seepage of water causes the velocity of the individual particle to increase. And what parameters affect boycott effect? Instability decreases the settling rate. And for our experiment, the settling rate increases with field angle as we convert from 0 to 50 degrees. And with smaller field angles, the clear fluid layer is thinner, which causes stronger instability. Viscosity does not affect boycott effect substantially, and by making the upper more rough, we can significantly decrease the settling rate for small field angles. And here are my references, and that's my presentation.
Thank you. Hold on, next question.
Okay, so can you show me the first diagram you showed of your experiment data?
The first diagram?
The very first diagram you showed us.
Okay.
Which,
I believe it's the vertical settling.
hold on. I'll stop with you.
Okay.
Right there. Wait, go back. Yeah, so you have the expectation lines and experiment data how to draw out, right? But it did match with the first three.
Yes, that's correct.
But why does it keep go down?
You're asking what causes this deviation right here?
Yeah.
Also, in our experiment, we rotated the container so that all the particles spread evenly, and this creates some vortices. And because not all of the particles are of the same size. Some particles stays and relatively at the top of the suspension.
Okay.
And that's what causes this decline. And that's what causes this deviation right here.
Okay, I get that. Okay, what else? Did you try different kinds of boycotts for your experiment?
Different, what do you mean by different kinds of boycott?
Like different kinds of particles.
Different kinds of particles. It's not included in my presentation.
Okay. Did you try it also?
I did.
Did it have any differences from your result in your presentation? Is there any differences?
Yes, there is a difference.
Well, okay. Do you think that the bubbles in your water may affect the final result?
What is this in my water?
Bubbles.
Bubbles. There aren't bubbles in my suspension layer. There are bubbles in my container.
Okay. How do you ensure the angel?
Nice. Okay. Preparation for component. The opponent is below.
Honorable judges and fellow opponents, I'm the opponent from Stanley, and today our problem is boycott effect. So this is a problem statement of boycott effect. If particles are suspended in a liquid that has a lower density than the particles. Excuse me. The particles will settle to the bottom of the container. The rate of settling can be affected by tilting the container that holds the liquid. Explain this phenomenon and investigate the effect of relevant parameters. And for us, our main focuses are to explain the phenomenon, investigate the effect of relevant parameters. Okay, so before we start to discuss of this topic, I want to give some rewind to our recorders. First, about the approach, they did very detailed data showing and really good diagrams showing on their presentations and some clear calculations that can be seen on the presentation. And for some cons that I believe they failed to achieve is that they didn't show the result of different particles. Since they have mentioned that they did the experiment in different particles, but they didn't show it to us. And I believe there is still some space to be discussed about what will affect this experiment within the different particles. And this is most of the points that I believe can be discussed. First is that, as I mentioned about the effect of the different particles. And second, I would like to, maybe later, I would like to understand more on the experiment they did on injecting the ink into the water to understand the flow of the liquid. I want to understand more on that part, so I believe that is something that can be discussed too. So I believe that is all of my presentation for now, and we can move on to the discussion. So yeah, first I want to ask to continue the previous question about will the different particles affect your final result of the experiment?
Yes, first of all, particle velocity is determined by its diameter and its density. So, for example, for a larger particle, the slope settling velocity will be larger. This will make the settling rate faster. And also, one very interesting phenomenon is that if we use a larger, if you use the particle with a faster sedimentation speed, then the clear fluid layer will also be larger. If we use a particle with a faster particle velocity, then the clear fluid layer will be thicker.
Okay. Sam, can you, okay, for the second discussion. Oh wait, can you show me what kind of particles that you use in your experiment?
It's silica sand, it's just basically sand. But the particle size is controlled.
Okay, how about the different particles? Oh, so it's basically just sands and you use different sizes of them?
You use the same size for all my experiments.
Wait, so you did mention about you tried different particles, right?
Oh, and that is not included in my presentation. Yes.
So it does well, if you use different particles, will it still match to your theory expectation?
Theory expectation? It will still match our expectation.
Did you have the data or did you compare them?
Well, I don't have the data in this presentation to show you.
You can show me, but did you do it?
Yes.
And they did match. Yes. Okay. Oh, I also want to discuss about. Do you think that the different liquid would also affect the result of this?
You mean different liquid?
Yeah.
Well, we changed the liquid type by adding glycerol to our solution.
Adding.
Adding glycerol. This has a larger viscosity than water, and this is also denser than water. So changing the liquid type influences the individual particle velocity. Yes. So in our experiment, here we change the fluid.
Yes.
And this is before scaling, and this is after scaling. You can see that it affects the settling rate, but after we scale it after we scale the time by the particle velocity, then after we scale the time, from these three graphs, we can conclude that viscosity does not affect much, and viscosity here is analogous to the type of liquid we use.
Okay, I understand. Oh yeah. So about your experiment, it's like we have to make the liquid start to have a little turbo in it.
As not like I just have to make sure.
Yeah, how did you start that?
Also,
How do you make the liquid kind of like stick?
even all the particles are suspended in the solution. So, for example, this is my container, and I will tilt it so that all the sediments are at the bottom, and then I will rotate it. And I will maybe shake it until all the suspensions all of the particles are in the suspension, and then I will to my desired angle.
Okay. So you did make sure that all the particles are in the range of the.
Yes.
Okay. Well, okay. So, do you have any purpose of? You can have a lot of ways to get the particles even, right? Is there any purpose of doing it that way?
So it makes our experiment easier. So, for example, you can see in our in this photo here, in this photo. Okay, this one's fine. So we can put a cap on my acrylic settling vessel, and this way I can tilt it, and after it all settles to the bottom, I can just shake the sediments up, and then conduct my experiment again.
Okay.
And I think there are other ways to make the particles suspend, and we could do that probably by stirring, but stirring will have the same effect, causing maybe even more vortices and causing maybe the spiraling motion of the fluid. And so we resorted to so we chose this way to make sure all the particles are suspended in our fluid.
Okay. You did try this experiment in different angles, right?
In different angles, yes.
Okay. So how do you ensure the angle is the correct angle that you want?
Okay. So actually for this experiment, you can here you can see that we have a background with paper printed with the lines, and we only have to match the container with the lines to know the angle.
I see. Did you ever consider to try even larger angles?
Have even larger angles?
Yeah, like 30 degrees.
We did our experiment up to, let's see, 50 degrees. And for 60 degrees and up, because the individual velocity of the particle is actually quite large, the particles settle to the bottom facing wall. They don't settle to the they settle to the bottom facing wall faster than they settle to the bottom of the container. So yes, then they settle to the bottom of the container. So we couldn't. Is it possible to get the data from angles larger than 50? Yes.
So you're saying that the effect will be not enough clear to be seen if the tree is bigger?
Yes.
Okay, I get that. Do you think that the different shape of the container of the liquid will finally affect the results?
Yes, that's actually a good question. So you see here in PNK, and may I draw on that sheet?
Wait, maybe you want to use the
Whiteboard? Okay.
Inside the blackboard is quite crowded.
So what PNK says is that the individual particle velocity stays the same. And let's say this is the suspension where it contains the particles. And because this area is increased when you tilt the container, the volume of water that is produced is also increased. And where does that water go? Water piles up here. So if I were to make the container thinner, it wouldn't change the effective settling area much. But it changes where the water has to pile up quite significantly. So for a thinner container, the water will only have to pile up for this area, and that would make the sedimentation rate faster. But for my experiment, I did not do this. Yes.
But so this is quite like your expectations for your,
That is it. What do you mean by my expectation?
you mentioned you didn't do different
Different
this kind of shape of the container, right?
Yes, I didn't change the width.
So is the previous speech mostly based on your expectations?
Well, what I'm trying to say here is that the sedimentation rate is increased by the effective settling area. So what I'm trying to say is an intuitive explanation of how tilting the container accelerates the sedimentation.
So can you predict the differences the differences between the different container will have a difference? So can you predict the different?
I cannot predict with my experiments because I did not do that part.
How about based on your theory?
So my theory is that I think there will be an optimum width. Because you see, PNK does not consider drag as I mentioned in my report. It does not consider the effect of instability, and also it does not consider the effect of drag on the container walls. And that's what I'm trying to add at the end of my presentation. That is, by making the aquamora, we can influence how the clear fluid layer rises. So, according to my experiment, this wall here also provides a drag to the rising of the clear fluid layer. So if I make my container very, very thin, then the drag will also be larger. And then that will impede the fluid from rising. So I think it will be an optimum width for the container.
Okay. I believe that is mostly all my discussions and thank you.
Summarize the discussion.
Excuse me. So now I will summarize my discussion with the reporter. I believe they did just like I just mentioned, they did a really detailed experiment and their theory is quite complete. So even there are some variables that is not considered in their experiment, they can still somehow predict the final result of this experiment within different variables. So I believe both their experiment and their theory is quite close to complete. Yeah, thank you.
And the review of the whole and for recorder, my first question I want to ask you, how do you define the settling rate that the problem statement requires?
The settling rate. So I define the settling rate by how much this top layer descends. How fast this
Okay, next question. And what's the shape downstairs on your container?
Pardon me?
What's the shape? Is curved or just a plane?
I mean the shape is settling.
A container?
The container is so it's a rectangle.
It's rectangle? Okay. And what's your concentration in your experiments?
So my concentration, I measured my particle concentration with volume fraction, and it's I added 1 gram of silica sand, and that is the boundary factor is 0.0044.
Okay. And what's the shape of the particle that you use for your experiment?
The shape, I believe they are mostly round.
Yeah. Okay. And how do you control height in H10? That
Yes.
the H. How do you control it?
Okay. Oh, H is not controlled. H is what we are trying to measure. So H changes with time. So that's why we have to integrate both sides to get how H changes with respect to time.
Okay. And for the next question, will the temperature affect?
Yes, the temperature affects the viscosity of the particles.
And part of the opponent thing.
Excuse me, can you repeat the question?
What will the temperature affect? Okay, next question for reporter. Do you think that the boundary angle, is there a boundary angle of your experiments?
Okay, my experiment, because my viscosity is actually quite small, there is no boundary angle. So the sedimentation rate increases with time. And the sedimentation rate increases with the tilt angle. But for really large angles, they mostly settle to the bottom base, which is hard to quantify. So does not match the problem statement.
Okay. And okay, my question is over. Thank you. Okay, good afternoon everyone, honorable judges and distinguished commuters. I'm a reviewer from Untitled Chapter, and today I'm going to review the problem 13 for point-up effect. Here's a summary of the report. First, the understanding of the problem. That first, they use tracker to track the particle speed, and they use the PNK theory to know the effective settling area will affect settling rate. And in a theoretical analysis, they use PNK theory to know the affecting settling area. And second, they use buoyancy of particles for a better model. And in the experimental confirmation, the tilting angle changes, the settling speed changes, and the viscosity increases, the settling speed decreases. And here's the reporter parts. The merits of the reporter is that they have a clear introduction to the problem, and they have an observation video. And second, they use luminosity to quantify the settling. And third, they use experiments to verify the theory regarding of drop speed, angle, and roughness of water, and the viscosity. And the possible next steps for the reporter is that first, missed address for rates of settling, and second, lack of investigation on area of container, temperature, grain size, and input experiment verification on their settling rate definition. And the summary of the observation is that the key insight of the opponent is first, the viscosity of the liquid's effects, and second, the ideal way to suspend the particles in liquid, and third, how the geometry of the container affect the results. And as the opponent parts, the merits are first, they have a clear speaking, and second, they ask questions regarding relevant parameters like the viscosity and geometry of container. And as the possible next steps, first is that they didn't ask the definition of the settling rates that is the problem statement needs, and second, more questions regarding myths like variables is temperature, collision of the particles. And as the discussion analyzed, the points that opponent asked is how to let the particles eventually evenly distributed, and the reporter's response is that it demonstrates how they do. And in our reviewers view that we agree with them, but because additional shaking may cause vortices. And in our reviewers question, that first is we ask how do you define the settling rates that the problem statement is, and the reporter answers that they define with the drop velocity. And in the reviewers view, we think that the suspended particles and the total particles is needed. And in second question, that we ask how will geometry of button tube affect the effects, that the reporter answered the rectangular and opponent didn't answer. And in the reviewers view that we think believes in addition to the tube area, the curved bottom end can yield higher convection rates. And the third question that we ask how different concentration affects the effect. And the reporter answered at 0.0014 and opponent didn't answer. And in our reviewers view, we think that the concentration needs to be under 10% or it will cause particles collision and induce vortex. And here are some missed points, and here were general suggestions. Thanks for your attention.
The reporter concluded remark.
General concluded remark. The opponent asked why didn't I conduct experiments for tilting larger than 50 degrees, and my answer is that it's error. Most sediments go through a lot of phase wall, which makes quantification really difficult. And this is related to the settling rate, which I will address later. And also, we made the arbitrary wall rough, so we think there exists an optimum settling rate, because there will be drag between the wall and the clear fluid layer. Also, and this was mentioned by the reviewer and the opponent, changing particle size influence the individual particle speed. And now on to why we define the settling rate to be, So here's why we define the settling rate as how the top layer declines. Because according to the reviewer's definition for settling rate, these two containers, if the particle velocity are the same, then the settling rate will be larger for this one. And we think that is not what the problem statement is asking for, because that is very intuitive. Because the effective settling area is increased. We think the problem statement is asking how the top layer of the particle change with respect to time. So that is why we chose to analyze the luminosity of the bottom facing wall, which is only influenced by the position of the top of the suspension layer. And that concludes my remarks.
Okay, question for jury.
For the reporter, the opponent asked you if you change the aspect ratio of your container, and you, what's the conclusion that if you increase, for example, the width of your, what will be the effect? Will you increase the sedimentation? Yeah.
Okay. So I didn't change the ratio in my experiment, but according to the theory, if this is larger, then the sedimentation rate will be lower. Should I elaborate on the whiteboard? So
That's your
that's fine.
expectation. You
That's fine.
didn't do the expectation.
Yes, I didn't confirm it.
What about the opponent?
I also didn't do this boycott effect experiment. So the question is, if the can you repeat the question?
What would be the effect if you increase speed in that diagram? The width of the container. Will it increase the sedimentation?
I think it will make this kind of situation to be a little bit more less easier to be noticed.
So you need to slow down the.
Not like slow down, but it will be like a bit harder to be noticed. There's this upward
It will either increase or decrease the
decrease.
process.
Decrease.
Decrease.
In our view, we think that if you increase the radius, maybe the radius of the container, the velocity of the particles will increase.
So it will be easier. It will increase the.
Yes.
Thank you.
Okay, I have one question for those three guys. Why you do the scaling effect?
And explain the whiteboard. So let's say this is the luminosity. This line here is the luminosity for maybe the particle velocity is 1, and this line here is the particle velocity. It was 0.5. So the reason I did the scaling is that it's pretty obvious that the cycling rate for the particle with a faster velocity will also be faster. And for boycott effect, I think what boycott effect is trying to see is how the sedimentation rate is increased with respect to its particle velocity. So if the two sedimentation were exactly the same, but only the particle velocity is lower, then if we divide the time by the time it takes for the particle to travel a certain amount of distance, then the two lines should look the same. This is to distinguish the effect of boycott effect and the effect of individual particle velocity.
Okay, for the opponent, do you agree?
Yes.
For the reviewer?
I agree with the reporter.
Okay. Now the score. Okay, for the reporter, please show the score. 8, 7, 9, 7, 8. Okay, for the opponent. Okay, 6, 6, 5, 5, 5. Very consistent. Okay, for the reviewer. 7, 7, 9, 7, 7. Thank you. Okay, we end this section.